Oh, all right. So we're back and we're doing more hypothesis testing. In section 10.3, we're going to be doing some hypothesis tests for the population mean. Back in 10.2, what we did on Tuesday, we were looking at the population proportion. So now we're looking at the population mean. We've looked at the population mean before and the sampling distribution for X bar, which is the best point estimate for the population mean. We've done a lot of work with this stuff. So we're going to be drawing on all of that here with the hypothesis testing. Now, the good news is that there's not a whole lot of new conceptual material here. Once we've tackled it, hypothesis testing in 10.2, here we're going to just be applying some of the same concepts, but with a new point estimate of X bar. Okay, so let's do a quick recollection here. Generally speaking, X bar, this sample mean, is normally distributed with a mean equal to the population mean and a standard deviation of the population standard deviation divided by the square root of the sample size, right? But in order for us to make this assertion that X bar is normally distributed with these parameters, we needed to know what the population standard deviation was. Now, generally speaking, if we don't know what mu is, then we probably don't know what sigma is, right? So generally speaking, then we're going to be using a t distribution to approximate the distribution of X bar, where since sigma is unknown, we're going to use the sample standard deviation S divided by the square root of n as an estimator for sigma. And so recall, once we add this additional estimator to the setup, that adds more variability to the probability model and thus forces us to look at a t distribution as opposed to an n distribution for X bar. Okay, so we will be using t distributions throughout these hypothesis tests. Now, to go over what we're generally doing here, what are the steps in general? First, we identify the hypotheses and the claim. For the population mean, you could have a two-tailed, a left-tailed, or a right-tailed test, right? And in which case, for your null hypothesis for the two-tailed, you have mu equals mu naught, whereas your alternate is mu is not equal to mu naught. For the left-tailed, it's the null is greater than or equal to, while the alternate is less than. And for right-tailed, mu is less than or equal to is the null, and mu is greater than is the alternate. All right, so these are all the possible flavors. Again, your book, for a reason that I don't really find satisfactory, doesn't write the null hypothesis this way, even though that's the obvious choice, but instead they just use an equal sign the whole time. So don't be confused by that. That does not change the way that we approach this problem whatsoever, okay? So once we identify the hypotheses and the claim, we know what sort of tests we're going to do. No matter what sort of test we're going to do, we need to compute the test statistic, T naught, which is given by X bar minus mu naught over S over square root of n. Once we have our test statistic, we then need to compare it to the critical values, which again, remember, are dependent upon alpha. So if it's a two-tailed test, then we're comparing our test statistic to T alpha over 2, which I'll show you how to get your calculator to tell you. And if T naught is less than negative or T naught is greater than positive, then we reject the null hypothesis. For a one-tailed test, we could either have a left or a right-tailed, in which case we're comparing the test statistic to negative T alpha for a left, or the test statistic to positive T alpha for a right. And if it's less than for the left or greater than for the right, then we reject HO. Okay. At which point, once we know whether or not we reject the null hypothesis, we can then draw up a conclusion. And we know how to do that. Let's see if I've got it in this pile. Yeah, we use our handy dandy flow chart. Okay, so use the flow chart to help us word our conclusion based on the various outcomes of our test. Okay, so that's the general structure, not really any different than what it was for the population proportion, except that now we're using a T distribution instead of the normal distribution to come up with our test statistic and our critical values. Okay, so I'm going to do one problem, because really one problem should be more or less sufficient to show you what you need to do. I will also go over some calculator stuff that will make this really pretty simple. Okay, so let's look at the following problem. So we're told that the mean height of American males is 176.3 centimeters. We're then told that the mean height of 44 US presidents is 180.1 centimeters, which is bigger, okay, with a standard deviation of 7.1 centimeters. The question is there evidence that presidents are taller than the average American male? All right. So that is what we're trying to figure out. All right, so let's do this thing. First, identify hypotheses. Who is HO and who is H1? HO would be that our mean is equal to the population mean. Right? Our alternate hypothesis would be that the presidents are taller than the average American male. So that would be that mu is actually greater than 176.3. Okay. And again, really, we could write this as less than or equal to. Either way. So once we've identified the hypotheses, we know that we have a right-tailed test. Now we need to identify the claim. What is the claim? The researchers are looking to determine whether there is any evidence that presidents are actually taller. So that would imply that, yet again, our claim is H1. All right. So now we know who our claim is, and we know what our hypotheses are, and we know that we're doing a right-tailed test. Great. Part 2, we need to compute the test statistic. All right. Now we can do this directly. T naught is equal to X bar minus mu naught over S over root N. So this is a rather straightforward computation. X bar is our sample mean, which is 180.1. Mu naught is the, I guess I should use mu naughts here just to be consistent. Mu naught is the population mean, which is 176.3. S is the sample standard deviation, which we're told was 7.1. And N is the sample size, which is 44. Okay. So that's how we compute our test statistic. We punch all that into the calculator, 180.1 minus 176.3, and then divide that by quantity 7.1 divided by the square root. Hold on. Why are you still here? There we go. By the square root of 44. Okay, so we get a test statistic that's equal to 3.55, thereabouts. Great. Now, we need to compare this test statistic to the critical values. Now, for a one-tailed test, for a right-tailed test specifically, we just need to find T alpha. Now, the alpha value has not been stated in the problem, which means we assume that alpha is 0.05. So to find this, remember, we use the inverse T function. And here we'll do 1 minus 0.05. And then we have to tell it what the number of, what the degrees of freedom are. Remember, the degrees of freedom is the sample size minus 1. So we do, to get this critical value, we do second vars, inverse T, then feed it 1 minus 0.05, comma 44 minus 1. And it gives us a test statistic of 1.681. Okay, so now we just need to compare this critical value with our test statistic. And what do we find? We find that the test statistic is greater than the critical value, right? So we have that T naught is greater than T alpha. So when that happens, we reject the null hypothesis. Great. So we've gone through the major computational steps. Identify the hypotheses, identify the claim, compute the test statistic, compute the critical value, then compare the two. Now we know to reject the null hypothesis. So the last thing that we need to do is come to a conclusion. So step 4, conclusion. And again, to get our conclusion, we use the flow chart. So is the claim H0 or H1? Our claim was H1. Do we reject the null hypothesis? Yes. Therefore, our conclusion is that the sample data supports the claim that blah, what our original claim was. So for us, the conclusion is the sample data supports the claim that mu naught is greater than 176.3, or in other words, US presidents are taller than the average American male. Full stop. Okay, so that's a full hypothesis test in this particular context. I whizzed right through it because honestly, it's not really any different than what we've already done. It's just now we're using a t distribution instead of a normal distribution. Now I will since I have the time, show you an alternate way to do this. Okay, so that we can sort of skip a lot of this stuff. Okay, so a completely different way of doing this. So this is the p-value approach. This approach can be used for the population proportion as well, back in 10.2, but I didn't want to go over it because I didn't want to overwhelm you. But this approach is arguably easier in some ways because you can use the calculator directly to kind of shortcut everything. So if we're doing the same problem, we'd still have to identify the hypotheses. Right, so the null and the alternate hypothesis. We still have to identify our claim. But instead of doing all of the test statistic stuff, what we'll do is do a, we'll use our TI 80 whatevers to do a t-test for us. So how does that work? If I hit the stat button, then cursor over to test, I'll see that there's a t-test here. Second option. Okay, when I bring that up, I get this menu and I've got a couple options here. I've got the input options, a mu naught, an X bar, a sample standard deviation, a sample size, and then what the alternate hypothesis is. So how this works is generally we don't have data we're working with statistics. So we select statistics and then we input all this information. So who was mu naught? For us, mu naught was 176.3. X bar was 180.1. Sample standard deviation was 7.1. Sample size was 44. And then our alternate hypothesis was for the right-tailed test. So all of this is already input the way we need it. So once you input all that, you hit the calculate option and it brings up a bunch of stuff. Okay, now we could use this. We could still do the same approach that we did before, not the p-value approach, but the test statistic approach. And this would spit out our test statistic. So we see that T naught is 3.55, which is what we computed directly. Not a difficult computation to do, but the calculator spits it out for us. So that's great. And we can then compare that to the T alpha value that we still have to calculate separately and get to our conclusion that way. But there's another approach, which is the p-value approach. You'll notice that there's a p number here, and that p is equal to 4.74 times 10 to the negative 4. So in other words, it's a very small number, 0.000474. Okay, now without telling you where this p-value comes from immediately, I'll just show you how we use it to determine the result of our test. All we need to do is compare the p-value to the alpha value. So there are two possibilities. Either p is greater than alpha in this case, or p is less than alpha. So these two options tell us either fail to reject HO, or reject HO. So for us, our alpha was 0.05. So we can see that 0.000474 is definitely less than 0.05. Oops. See that? Yeah, there we go. Is definitely less than 0.05. So just using the p-value approach, we could see that we would reject the null hypothesis. Now, there's a great mnemonic device for remembering this approach, and it simply said, if p is low, reject the HO. Okay, so if p is less than alpha, reject the null hypothesis. If p is low, reject the HO. Hard to forget that one, right? So this is a totally valid way of doing it without using test statistics, without using critical values. You do have to either compute the p-value directly or use the calculator to generate the p-value. But this is a totally good way of doing it, right? This approach can also be used for the for population proportion problems, but the only difference would be that instead of doing a t-test, there we would do a come on, zoom in now. There we would do a z-test, because for the population proportion, we know that we have a normal distribution. So here you would input all of this information as you need it, very similar to what we had for the t-test. And I'll put something realistic there, I don't know, 1. Yeah, I mean, it doesn't directly apply here, but just showing you how you would do it. Bring up the t-test, hit calculate. Stats test, z-test, calculate, right? And same idea, the z-test will spit out a p-value, and then you can compare the p-value to the alpha value, and if p is low, reject the HO. So we can use this p-value approach for population proportions as well as population mean problems, hypothesis test. So that's the p-value approach. In some ways it is easier, especially with the aid of the calculator. So there is no preference. You can do the critical value approach, the p-value approach, whichever one you prefer. Okay, so I think that that's really enough for 10.3. I will be assigning a homework and a quiz this week. It's Thursday, so I'll be signing it soon. And so keep your eyes peeled for that. And next week should just be a review week. So yay. Take care.